All right, guys, here we go. So we are going to be looking at section 6.3, volume by slicing. Oops, that's not helpful. Okay, so let's kick it old school here for just a second. And remember when we were looking at finding integrals, right? And we did our Riemann sum because what we were saying was it was the area from this point to this point, and we were just adding those up. Well, that's what our volume by slicing is going to be. So whenever I'm looking at this, let's zoom in a little here. When we're looking at this figure, right, whatever this ends up being, we can slice this up, and then we're going to take each one of these pieces, right, and then we're going to add those up. So the area of this one plus the area of this one plus the area of this one, etc., right? Now the same kind of thing is happening. If I inevitably want this to be my figure here, this is not truly indicating what my figure is. The same concept here that we were looking at whenever we were looking at those integrals, where I want to have infinitely many slices. Because we are having infinitely many slices, that's where we come up with this integral, right? As you increase the number of slices, that's when you get that nice smooth curve, and that's where you get that integral. The same concept. I'm just bringing what we did previously into what we're currently looking at, right? Okay, so check this out. Here is the general slicing method. We are going to take a solid object from a certain point to a certain point. So where x is equal to a, to x is equal to b. So whatever those are, right? And then my volume here is going to be this integral from a to b, because remember when you talk about integration, you talk about from the small to the big, because that's what's in order. Capital A of x dx. Now remember, it's important, super duper important, to put this dx on there if x is the variable that you're talking about, right? And the whole purpose of that a of x, here, let me move this down just a tad here. The purpose of this a of x is because this is the general, this is the generic, right? That's what we said, the general slicing method. So anything that we want to look at, that's where this a of x is going to be the area of that slice. So anything that we have, we can take the area of whatever that slice is, and then I have infinitely many of those, right? Because that's the concept of the integral here. Infinitely many of those so that I can look at it. For instance, check this out, right? If I have this figure, I can look at this slice right here. So I want to find some formula that's going to be a nice slice that I'm looking at, and then I'm going to add up those infinitely many of those slices, and that's going to make this curve. All right? Okay. We are going to look at specific methods in this particular class, so like what we're doing right here, but it's good to look at this general slicing method because this is general to anything. So any object you want to pull off, you figure out what the area of a slice is going to be, and you can find the volume of anything. All right? For our intents and purposes, we are going to look specifically at a couple of different methods revolving around different axes. All right, that's what we are going to look at specifically. All right, so take a look here. So we are going to do a disk method is the first one that we're going to be looking at. So the disk method about the x-axis. All right, we are going to let f be continuous. with f of x, oops, I ran out of room there, is greater than or equal to 0 on the interval from A to B. Okay, if the region R, we're going to denote it as R, bounded by the graph of f, the x-axis, and the lines x equals A and x equals B is revolved around the x-axis. Then the volume of the resulting solid is given by this. I'm going to suck this in a little bit. Resulting solid of revolution, right, because it's revolving around there, is given by this formula. Volume is the integral from A to B of pi f of x squared dx. Now, let's talk a little bit about this because here's our formula, right? So, if f is continuous with my function, so my output values, right, my f of x values are greater than 0. That means I have positive outputs, right? My positive output values, all right? Okay, output being the y value in this instance. On the interval from A to B, so it's above the x-axis on this interval from A to B. That is why if my region is bounded by the graph of f, so this is my output that's positive, the x-axis, because we know it's not below there, and the lines x equals A and B, because that's where we're starting and stopping, is revolved around the x-axis, then the volume of the resulting solid of revolution is given by this integral. Let's look at this here for just a second. Now, I'm going to do my best to draw this picture. Bear with me, y'all. This is just how it rolls. I'm going to make this bigger so you can see this here. Okay. Now, let's say that here is A right here, and here is B. All right? And my graph is this for no other reason other than just the fact that that's what my graph is going to be. All right? So here is what's happening. I am going to take this graph and then I am going to swing it around the x-axis. That's what we're talking about whenever this says the volume of the resulting solid of revolution. If the region is bounded by the graph of f here, so it's bounded by this graph of f everywhere it goes. Down here, it's bounded by that graph of f. The x-axis here and the lines A to B. So it's that's what we're talking about here. Then this volume is what you get whenever you swing that thing around that x-axis. All right, so let's see how good I can pull this off. So I need to go to about right there. So let's say that that's what's happening there. This, oops, try again. Is going to be kind of like this 3D figure. Do you see what's happening here? I know I'm not very good at drawing. So here I have this is revolving around this axis. Do you see that? As we're coming around this axis is what's going on. Let me put it out here. Coming around this axis. And that is what's making that solid. So this is kind of like a, I don't know. I'm not going to say a bowl because you think of the inside is out, but it's this solid before you take the inside out of your bowl kind of laying on its side. Do you see that? That's what's going on here. And this is just winging this graph, right? It's all different. But check out what's going down here. This is what I really want to point out. If you were to look at this straight on, what shape will be made? Like assuming that you're looking at it straight on and we're using our nice good imaginations. This is revolving around that x-axis. What shape is going to be that slice? Yeah, a circle, right? If I'm swinging around there, then my slice at the end of that is going to be that circle. So check this out, you guys. What's the area of a circle? Pi r squared. You're exactly right. So if it's pi r squared, what just happened? Pi, and this is squared? What? We're using previous information into this current lesson? Well, of course we are, right? Check this out. And here's the reason why I have f of x squared in terms of my radius, right? Because my radius here is going to be my function. You see that? My radius down here close to A is not going to be as big as my radius out here close to B just because of how my function is. So I can't have a set radius. This circle is going to be bigger than this circle down here. You catching it now? Yeah. So this slice is going to be a different area than this slice, which is a different area than each slice as I go through my solid. That is why it's important here, if I have the radius of this circle, it's whatever value I have coming up to my function between A to B. This is simply the area of a circle. And your radius is dictated by where you're hitting your function. Pretty sweet, right? All right, let's do some examples.